So we're going to talk about the space vectors, module number 4. We got 2 more modules to go before we end the day. So here now we want to introduce mathematical constructs so that we can simplify our math. One of the mathematical constructs we want to talk about is called the alpha beta axis, where the idea is I want to have an alpha beta axis on the stator and I want to have a dq axis on the rotor. Okay. And this is going to be, I have a deliberate mistake in this, not a mistake, but I have a deliberate part which I want you guys to pay attention of in this whole mathematical construct. And that part is theta, the relationship between the alpha beta axis and the dq axis, right? So the mathematical construct is we want to be able to reference all the stator quantities on this two-phase reference frame called alpha beta and all the rotor quantities on this rotating frame called dq. And we define the relationship between the dq and alpha beta with an angle called theta. Now, theta in this case is angle between the d-axis and alpha. Okay. Now, you can also define, and you will see in the math later on, how you define the relationship between alpha, beta, and dq axis is going to define all of your equations, Clark transformation, Park transformation, etc. So if you do the basic math here, if I take a projection of ID on alpha and beta, so I have ID cos theta minus IQ sine theta. This is ID, right? I alpha. Sorry, I alpha, ID is here. Yes, so I alpha cos theta minus IQ sine theta. Is that correct? Is that correct? And then I beta is ID sine theta plus IQ cos theta. So along the axis, I have got ID cos theta, and this is a negative component, IQ sine theta from here. And then along the beta axis, I have ID sine theta, this projection here, and then plus IQ cos theta. Okay, so I think these are correct equations. So this is my first construct I want to talk about. And then I want to increase the complexity. And now I have got A, B, C vectors. A, which is aligned with respect to alpha. And then we have IB, which is 120 degrees away from IA. And then I have IC, which is also 120 degrees away from IB and IA. Now, what I want to do is I want to resolve these three currents, three vectors into two-phase, okay? So I do the projections here, and the projections I do is, since IA and alpha are aligned, IA is equal to I alpha. And then I take the projections of IB on beta axis, and I take the projections of IC on beta and alpha axis, essentially. And these are my equations. IB is equal to minus IA cos 60, okay? And then so this is the projection of IB on IA and the projection of, so I'm transferring, sorry, I'm doing it wrong. So I'm projecting alpha and beta onto IB. That's what I'm doing. And I'm projecting alpha and beta on IC. These are the components of alpha, beta on IC. Is that correct? Yes. So IB, so I take a projection of IA onto IB. So this is 60-degree angle here. That's correct. So I take a projection of this axis on this axis because this angle is 60 degrees. And then I have projection of IB, and this angle is 30 degrees. So this is correct. So I am projecting alpha, beta onto IA, IB, and IC. So these equations come out to be pretty simple. So you can see IA is equal to I alpha, IB is equal to minus 0.5 I alpha, and then 0.87, which is cos theta. So I think these are pretty basic equations from that standpoint. And then, so here is the extended math, where you have now alpha beta in terms of IDU IQ, I A I B I C in terms of I alpha I beta, And now I can actually have IA, IB, IC in terms of IDIQ. Okay. So this is how we can transform our three-phase into two-phase math. All right. So this is the fundamental equations from that standpoint. And I can basically now have IA, IB, IC equal to a matrix like this, IDIQ. All right. So, or I can do IDIQ in terms of IA, IB, IC. So now I've taken my three-phase currents and transferred into two-phase currents. Okay. And now the theta is obviously the rotation of the rotor with respect to the stator. So this is what's happening inside the motor when we use this math. Okay, so this is your alpha beta stationary axis, and this is essentially your space vector, which is sum of ID square, IQ square. Okay, now here is your rotating. Now, if you do a rotating frame reference DQs, your rotor is rotating, alpha beta is stationary, and then you are creating a space vector which is rotating in the synchronous DQ reference frame, right? So that's what's happening inside the motor. So the magic is, now you have to remember the very first slide we started with, that you have got, you're trying to get back to the simple math where you say, okay, using the right-hand rule, if I have a flux density going this way and I have a current going this way, my force is this way, right? And that force causes a rotation, okay? So we are trying to go to the D-axis and the Q-axis, and that's how we are trying to solve the math. We are trying to simplify to the fundamentals so that we can simplify the math in controlling the motor. And you will see how that translates into algorithms and gives you much more dynamic response in your algorithms when you use the simplified math. All right, so here on the left-hand side, you essentially have no alignment of your, it's an arbitrary orientation. That means your axes are not aligned with respect to D and Q, okay? So when you're not aligned with D and Q, basically you're floating, you're still stationary with respect to DQ axis, but you still have the lambda R, the flux producing, the magnet produced by the magnets, and then you have the current. IS is the controller current produced by the controller, right? We've seen this torque equation, which is a cross product now between lambda R and IS from our first fundamentals. And then if you align your lambda R with your D axis, then you can see how the same thing is shifted, and you can see how it is oriented on rotor flux linkage. So that's why it's important to visualize or do the math with the proper orientation. And I'm going to give you an example of that, is how critical it is to orient your magnet with respect to the D-axis, right? If you don't orient your magnet with the D-axis, your math is going to be all wacky. All right. So now this is homework if you want to take this on, develop a spreadsheet where if you have got, let's say, 3 Hall sensors in a motor, okay, HA, HB, HC, and you need to, your back EMF vectors are here, so your current has to be aligned like this. You can assume your HA is leading your back EMF by 90 degrees. This is your anti-clockwise motion. And then your, in the clockwise motion, obviously your HA is leading or lagging with your back EMF or your current. So you could essentially develop the equations where you take your Hall sensors as 0 and 1. They switch every 180 degrees, assuming you're between north and south poles, and then develop your equations where you have. So what I would do, and let me show it on the screen here, and this may be a fun exercise to do if you have time. So let's go back to the drawing board. All right, so normally what you're looking at is you can develop an Excel sheet where you have got in the first column angle, and you can go 0, 1, 2, etc. And then you can have your back EMF waveforms, EMF, B, C, and you can call this as sine theta, sine theta minus 120 and sine theta minus 240. Okay, that can be your, and then you can convert the next few columns, you can then do IA, IB, IC, which can essentially follow your same profile as EMF, and then you can calculate your I alpha, I beta, and then you can calculate your ID and IQ. Now, obviously, ID should come out to zero when you are aligning with respect to the back EMF. When these currents align with the back EMF, your ID automatically should come out to zero. You only should have IQ here. And when you do a phase advance, where you can now actually put a different theta here, then you will see that ID begins to emerge. Okay, and these should be DC values, and I alpha obviously should be equal to IA, right? So this would be a good exercise to do. Oh, I guess I lost my screen. Just a second, screen for some reason. So all right, so let me repeat one more time. I don't know how much of it you guys got and when it stopped. So I could develop an Excel sheet where on the first column, I have just angle in degrees going from 0 to all the way to 360 degrees. And I could also, and then you have EMF, you can align the EMF such that you have sine theta minus 120, sine theta minus 240. And you can essentially compute your IA, IB, IC to be in phase with this. You can put any magnitude you want, and then compute alpha, beta, and then compute D, ID, IQ. And you will see that ID should come to zero under base speed. You'll have IQ, some value. These should be DC values. So you could also see a relationship in terms of, then you can also put Hall sensors, Hall B, Hall C, where, for example, Hall A is leading by 90 degrees, right? So if I take this back EMF signal and you're leading by 90 degrees, you're going to start, so this is your, so you're going to, this is your 90 degrees. So my Hall sensor signal is going to emerge from here. It'll be 1, and then it'll be 0, and then it'll be 1 again, right? So you could also, so this is a 0 degrees, this is your 360 degrees. So you could also write down your Hall angles. So Hall A will be 1 from 0 to 90. Then it'll be 0 from here to 270. Okay. So all of this you can create in one Excel spreadsheet and play with the numbers, and then also do field weakening by advancing the current from back EMF and see that your ID will emerge. Right. So this will be something, if you're playing with Hall sensors and trying to figure out the alignment of the current, etc., this can be a useful exercise for you to do. Okay, so let's get back to, and then you can do the same thing in the clockwise motion and set up all the equations so you can understand what's going on. The beauty of this is you can actually compute all of your efficiency numbers as well. It will automatically show your power output, because when you multiply the back EMF with the current, all three, I1, let's say IA, EA, IB, EB, and IC, EC, will, they add up to a constant number, which is your power input to the motor. All right, so any questions on that aspect?